that high, the life and the reliability is very good. Now let's go to the other material. Now you have again the slide. And this is the titanium oxide. Very interesting material. Is a kind of brookite structure, rather dense. So to have to remove lithium from here and to insert it back, you have actually in the opposite. Put lithium inside and to remove lithium in these holes here, these channels here. You must assure that lithium diffuses inside this structure. And if you prepare this structure in the normal way, it is difficult to have a very fast electrochemical reaction. So what is the way as to make this material feasible for battery is to go into nanostructures. And this is a very common approach now in the electrotechnology. Why you want to go to a nanostructure? Well, suppose for instance, look for instance these TM pictures, and you see that this indicates, this illustrates the structure that have been adopted by this electrode, and this is a very thin wire. Nano wire, when we go to nano technology, we have to go into 10 to minus 8 that one is 11 centimeters. So it's very, very, very little. Okay? And then, for instance, take this fiber here. Now, the process, the electrochemical process is to insert lithium here and to remove it. Now, if you have such a very thin part, the diffusion of lithium is very easy here because it's very short. If you go to a big chunk, you will have, of course, some difficulty. So this is a typical example how nanotechnology can help in increasing the rate of some electrodes. And here, in fact, you see that this is the process that we are looking for. And in charge, we will have the lithium ion getting into the structure here and forming lithium titanium oxide, and in discharge is just the opposite. And here you see some typical discharge curves. Okay, this is okay. If we use bulk titanium oxide, namely very large particle, then we have the diffusion problems that I mentioned before, and the curve is this dotted one line. You see that we have a limited capacity and some hysteresis between charge and discharge, typically indicating we have some kinetic. However, if we pass to titanium nanotubes, but even better with titanium nanowires, you see that now the charge and discharge curves are much more close together, so there is not a big hysteresis, which indicates the occurrence of some overvoltages, and the capacity that we get is approaching the theoretical capacity, 300 milliampere per gram. So titanium oxide can be used as nanomaterial, but it requires the preparation, usually it requires the preparation in nanostructure, like nanowire. Of course, there are also some drawbacks going to nanostructure. If you take this picture here, you will see that now we will have a very thin diameter, and this improves electrochemical process, I say. But also we will have a very large surface. You can imagine that with the surface has a lot of these wires, okay, like a brush, but with a lot of wires. So the reactivity increases also. So if the nanostructures will give you some advantage in rates, they may be unwanted because they can produce some problems in safety. But we'll discuss this later. Now let's compare now the properties of this titanium oxide anode with respect to the graphite. As in the case of titanate, we have some drawbacks. It's a higher voltage, here, which is 1.5 volt versus 50 millivolts, as in the case of titanate. The lower capacity, the capacity is higher than that of titanate, but still a bit lower than graphite. However, these drawbacks are contrasted by some important advantages. First of all, titanium oxide is at a very low cost, because titanium is largely available in nature, so it's an abundant material. And titanium is, of course, environmentally compatible, and a very high power capability because it's produced in this nanostructure. And also operates within the stability window of the electrolyte. So this results in a higher reliability, higher safety, and higher power with respect to graphite. This is the reason why we have this interest now with this material. However, the most appealing, you have this one, right? Yeah, the most appealing materials at the moment are these lithium metal alloy. Why? Because if you take now this value, which are graphite, we have 370 milliampere per gram energy capacity in terms of weight, and 855 milliampere hour per cubic centimeter. So this gives you the capacity per weight, and this is the capacity per volume, and this is the potential. Okay. Now, let's take, for instance, this material. This is the alloy of lithium with aluminum. So here, actually, the electrode is formed by aluminum, which takes lithium as an alloy and releases lithium. And the capacity is about 800 milliampere per gram, much higher than this one. And also the capacity for volume is much higher than this one. And the voltage is a bit higher, but not that high. So it's compatible. Let's take now this one, which is the alloy with tin. What is this tin doing? It can accept lithium up to 4.4 equivalent per mole. This gives you a capacity of 900 milliampere per gram, three times this one, and 1000 milliampere per cc. And the voltage is also. But the most important, of course, is this one. You can see that now we have silicon. Silicon can alloy lithium up to 4.4 part per equivalent, like this one. But look at the capacity now is 1 order of magnitude higher than graphite. So everybody now would like to have replace silicon with graphite, because silicon is very abundant, doesn't cost too much, and the potential is very low. What will happen? What happened? What are the problems that so far have prevented this material to be practically used? Well, here you see some sketch of the model. So when we take some lithium, suppose this is the initial structure of silicon or maybe tin. Now when we use some lithium inside, and lithium is blue one, no, excuse me, lithium is this gray one here, we will have very large expansion, volume expansion of silicon or tin or aluminum. You see here, we report here the volume expansion that we obtain from when we use the electrochemical process, so when lithium is inserted in the metal. You see that if you make a lithium aluminum electrode, we have 100% volume expansion. Forget about this one. Tin is 250%. Silicon is 300%. While you see graphite as maybe a little one, and you see here, most important, titanium oxide is practically no expansion. Why this expansion is so bad? Because you understand that if I have this silicon electrode, tin electrode, and I expand it so much with some lithium, and then it shrinks, it's reduced when I remove lithium, and we do that upon cycle, this big volume expansion creates some volume tension into the material, and the material breaks, and we cannot cycle for a long time. You see some example here. You see that this is maybe the structure of one of these, whatever, aluminum, silicon or tin, the problem is all the same. And you see that before cycling you have integrity of the particles, but even after 2 cycles you start to see some break here. And after 5 cycles it's completely collapsed. Then because of this large volume variation, you have these breaks. So what will happen? That the electrode breaks, it forms a small particle that fall down, and they are lost for the electrochemical process. So the capacity goes down. So how can we solve the problem? Or better, how the problem has been solved? The problem has been solved again by going to nanostructures. For instance, let's take this example here. This is related to some silicon. You see that instead of preparing the electrode of silicon, we prepare the electrode in forms of pillars, like this one, nanopillars. So suppose that this is this here in this model is the current collector, piece of metal, and on top of that we create these nanopillars. Suppose that this is about 100 nanometers diameter. Well, also in this case, of course, and here you see some the picture of actual morphology taken by SEM. Well, you see that, of course, the volume expansion is an inherent property of this material. So we will have volume expansion also here. But the difference with the compact structure is that there is a lot of space between the pillars. See also here, the picture. So this space